So in this part, we're talking about the shapes of graphs continued. So it's just a continuation of our lesson. We learned the basic concepts, now there's a few more technicalities. But to start with, on each problem you should be telling me as much as you can about the shape of the graph. So even if I'm not saying it explicitly, you should always be looking for increasing, decreasing, max, mins, concavity, inflection points, etc. So first, we have times where we might have a graph that doesn't actually have a max or min. So if you look at this graph right here in example 3, notice you're not actually going to have a maximum or minimum, right? Let's see what happens if we were actually to try and find one. So you'd find your first derivative. Okay, and let's see, so we have negative x cubed plus minus 8. So our first derivative would be negative 3x squared. And that's it, just negative 3x squared. And so if we set it equal to 0, that would tell us that x equals 0. So our critical point is x equals 0. That's the possible max or min. Okay. Then I draw my number line. Here's my 0. And I try and plug in some points in there because either side, so negative 1, positive 1. So f prime at negative 1 would be negative 3 times negative 1 squared, or negative 3. And f prime of positive 1 is negative 3 times 1 squared, which is 3. So negative 3. So either way, this is negative and this is negative, so we're going down, and then we're also going down. That's kind of interesting, right? We haven't actually looked at anything that's like that. So we're actually decreasing for x less than 0 and x greater than 0. And if we were to look at this picture, just remember we decide if it's max or min just based completely on the picture. And if we look at the picture, does that look like a max or min? It doesn't look like either one. It wasn't a picture like this or a picture like this. It's neither one. And so this is actually not a max or a min at x equals 0. So what actually happened here? When you look at your graph, notice here at x equals 0, our graph is kind of flat. So it's kind of flat like this. It's neither a max or min, it's just a place where we happen to have a slope of 0, and then we just kept going down. And then in case you were wondering, let's go ahead and find our second derivative. Our second derivative would be negative 6x, and if we set that equal to 0, x equals 0 is our possible inflection point. So everything's kind of possible until we decide for sure if things are changing. So here's our 0, and you should pick a point on either side and plug it in your second derivative. I'm running out of room to write it, but if I put my negative 1 into my second derivative, I get negative 6 times negative 1, which is positive. So I should be kind of looking like a U shape. And at positive 1, if I plug that in, I get a negative, so I should be going down like this. Notice that is what happened on our graph. We were kind of a up U shape, and then we changed to down U shape. So concave up for x less than 0, concave down, x greater than 0, and that gives us an actual inflection point because we changed concavity. We have an inflection point at x equals 0. So, graph of f prime of x. Sometimes we'll actually look at the graph of the first derivative and try to deduce information about our original function. So again, this is our derivative, and f of x is our original. So let's look at our graph of our derivative down below and try and sketch a rough graph of f of x. Now when we say rough, our shape is not going to be exactly correct. And we don't really know how far up or down we are. This is just very rough with kind of general shape. So coming over here, what do you notice? This is the derivative. Not our actual normal function, but our derivative, which tells us slopes. So that means at 1, when x is 1, we had a slope of 2. Okay. At x equals 2, we have a slope of about 1. At x equals 3, we have a slope of 0. And at x equals 4, slope of like -2. Okay, so notice we did do a couple things here. When was our slope 0? At 3. So we have a critical point at x equals 3. And if we pick a point on either side, like 1 and 4, at 1 my slope is positive, so I'm kind of going up. And at 4 my slope is negative, so I'm going down. So that looks like we're going to have a maximum. So max at x equals 3. So at x equals 3, kind of drawing, you're going to have a maximum. Okay, let's see. At x equals 1, my slope is 2. At x equals 2, my slope is 1. So I should be a steep slope at 1 and a not so steep slope at 2. So I'm kind of going like this. And at 4, I should have a slope of -2, which is kind of steep, but I'm going down, which makes sense. If you had a maximum, we had to go up and then down. So that's what you can kind of tell looking at the graph of just our derivative, is that my original function looks something like this, with a maximum at 3. Now, for different types of extrema, an extremum is a maximum or minimum, and if you have more than one, we call it extrema. So you'll see that word as you do your homework. Now, there's two different kinds of maximums, and similarly minimums. So you can have a local or a relative maximum, which means that it's higher than any other points nearby. Or you can have an absolute maximum, which is higher than any other point on the graph. So let's look at a picture. Notice this picture, we kind of go up and down, up and down, up and down. It's quite the mountain range. Every time I have kind of a peak, I could call it a relative max. So we have a peak and a peak. So those are both relative maximums. Even this is a peak, so that would be a relative maximum. And anytime you have a valley, that would be a relative minimum. But you also look at your entire graph and find the highest point anywhere on the graph, and that's your absolute maximum. And the lowest point on the entire graph is your minimum, absolute minimum. So it turns out that your relative maximum can also be an absolute maximum. Like here, it's a peak, and it's the highest point on the entire graph. And why do we make the distinction? Because we can have more than two or more relative maximums, but your absolute maximum is going to be the highest point. Sometimes it's at a relative maximum, but sometimes it's at an end point, which is the case here for this absolute minimum. It wasn't actually a valley. You didn't go down and then up. You just stopped. So that's where we're at the end of our range, but it is the lowest point on the graph, so it's considered our absolute minimum. So in this example, we have f of x equals x cubed minus 12x for x that goes between -3 and 5. We want to find any local and absolute extrema, max or min. And on this case, we actually want to find our actual point and not just the x value. So if you remember back in other math classes when you took like Math 1050, you had to go through and you had to find an actual x and y values to give you a coordinate pair. You can just say where the x value was, you had to say the entire point. So we're actually going to do that on this problem. So you always start by finding your first derivative. So it would be 3x squared minus 12. Let's set that equal to 0 and solve for x. So x is going to be 12 out of 3 plus or minus 2. And these are our critical points. So you draw your number line. Here's my 2. Let's plug in a 0. Let's plug in, you can pick any number you want. Let's do 4. So f prime of 0 is going to be 3 times 0 squared minus 12, which equals -12. So that's a negative, so I go down. And f prime of 4 is 3 times 4 squared minus 12, which is 36. So that's positive, so we're going up. Oh, what did I do? That was a plus or minus 2. I also need a negative 2, which means I should also test, let's say, negative 4. So f prime of negative 4 is 3 times negative 4 squared minus 12, which also equals 36. So positive, and we're going up. Okay, looking at my picture here, we have what we would call a relative maximum, because we go up and then down at x equals negative 2, and a relative min at x equals, let's see, minimum, we go down and then up at x equals 2. But where are our absolutes going to be? So what you do if you want to know your absolutes is you check your critical points and you also check your endpoints. So again, you have to check critical points and endpoints. Okay, so let's see what our y values are. So at my relative max of x equals 2, what we want to do, if you want to see what your y point is, you plug it into your original function. So f of negative 2 is negative 2 cubed minus 12 times negative 2, which is 16. And you plug 2 into your original function as well. So 2 cubed minus 12 times 2 is negative 16. And you also plug in your endpoints. So our endpoints are what? Negative 3 and 5. So f of negative 3 is an f of 5. So let's plug those in. Okay. So we found that f of negative 3 will be at 9, and f of 5 will be at 65. We know what our values are for our max, relative max, and mins. So now you just go through and pick what is the absolute highest point. So our absolute max is the entire highest point, which is a 65. So it's at the point 5, 65. And our absolute min is your lowest point you see for negative 16 at the point 2, negative 16. Okay, and let's just go ahead and rewrite it. Our relative min is 2, negative 16. And our relative max is negative 2, 16. So let's go back up and make sure that matches with our picture. So at negative 2 and positive 2, we had relative max or mins. But our highest point on the graph is way over here at 5 because it just kept going up and up. But this endpoint is not an absolute minimum because it's not the lowest point. This point is. And notice here, when we wanted to find the y value, which equation did we use when we wanted to find the y value? If you want to find the y value, you plug x into the original function, f of x. Okay, so that's important to know. Usually you get so used to working with your derivative, you forget to plug it into the original function when you want your y value. So in this next part, we're going to talk again about how our graphs are related, and it might feel like we're just kind of doing the same thing over and over, which is because we are. Okay, but notice this box. This box is very important. You should probably memorize this box, or at least print it off and put it next to your desk while you're working on your homework. Okay, you'll want this box. So it's just kind of a reminder. F of x is your original function. F of x gives you the y values, or the height of the function. Okay. Now f prime of x tells you the slope of your original function. This also means then, if it tells you the slope, that our first derivative also tells us if our original function, f of x, is increasing or decreasing. And f prime of x, wherever your first derivative is equal to 0, that tells you the critical points where there might be a maximum or minimum. And the second derivative tells you the concavity of the original function. So that tells you if your original function is concave up or concave down. And wherever it's equal to 0, that's the possible x values for inflection points. So again, that's what all of our functions do. That's something that you should memorize or at least be very familiar with. So let's kind of look at some of these graphs. We're not actually doing anything on these problems. I'm just trying to get you familiar with it. Okay, so in this, we have our original function f of x, our first derivative, and our second derivative. Notice they went through in our original function and they measured the slope at several points, so you can see the tangent lines. So we have a slope of 18, then 6, then 2, then 6 again. So we're really steep, and then not so steep, not steep, steep again, etc. So you take these numbers, so when x equals 0, our slope was 18. So if you come over here to your first derivative tells you slope, right? So at 0, our point is actually 18. That matches our slope of our original. And when x equals 2, our slope is 6. So you go over to 2 and up to 6. So you're putting your slope values over here as now your new y values. And at x equals 4, we had a slope of 2. So 4 and 2 and 6 and 6. So these slope values are what we put in for our first derivative, because your first derivative tells you slope. And your second derivative tells you concavity. What this would actually be is if you took the slope values of this function and put them over here, that's how you'd actually get to your second derivative. But let's go back and look at a few things here. So when you look at your first derivative, notice the first derivative is positive everywhere. So it's positive for all x. So that means f of x is increasing for all x. Does that make sense? Yep, it was increasing for all x. Okay, let's see. And now when you look at your second derivative, notice your second derivative is negative up to 4 and then positive. So f prime of x, double prime of x, is negative for x less than 4, and f double prime of x is positive for x greater than 4. So that means concave down for x less than 4, and concave up for x greater than 4. So let's look at our picture. So here's my 4. We were concave down, yep, and then we were concave up. So you switch from like an upside down U to a right side up U. So all of those graphs kind of match up. Also, every once in a while, you'll get a problem where you might be interested in the first derivative. And so if you take the first derivative and you take the derivative again, you get to the second derivative. So you could ignore the original function and pretend that your first derivative was your original function. And if that was the case, and you need your original function, notice, is there a minimum here? There is. And so that would have to be where your derivative changes from positive to negative. So if this was your original and this was your first derivative, notice the first derivative, or the derivative here, would be equal to 0 at 4, which is where we had our minimum. And it was negative, or decreasing up to 4, and then it was positive, or increasing from 4 on. So every once in a while it will ask you a question about, like, when is our slope increasing or decreasing, and you could just take the derivative again. But that's kind of confusing. Okay, you have to really think hard about that so you don't get confused. So now let's look at our graphs of f of x, f prime of x, and f double prime of x, and describe the shape of f of x. Notice I did also tell you where your critical values and possible inflection points are. So f prime of x is 0 at 0.87 and 10.1. F double prime of x is 0 at x equals 10. So we have f of x, f prime of x, f double prime of x. So let's talk about where are we increasing and decreasing. So to do that, you would look at our first derivative, which tells you slope. Our first derivative was 0 at 0.87 and 10.1. I don't know how I got 10.1. I just typed that wrong. That's supposed to be 19.1. That actually matches what we have on our graph. 19.1. Okay. And so if we were to draw our number line, it looks like to the left, our slope, our actual slope values are all negative values. So we're negative. So my original function is going down. Not the actual first derivative, but my original function. And then from 0.87 to 19.1, our slope is positive. So our original function is going up. And from 19.1 on, our slope is negative. So our original function is going down. Okay. So it looks like we would have our original function is increasing for x between 0.87 and 19.1, and it's decreasing, let's see, for x less than 0.87 and x greater than 19.1. Okay, now look at your original function. Does that match up? Here's my 0.87. Here's my 19.1 is about here. So we were decreasing, then increasing, then decreasing. So that matches. And we're going to have a max. Let's see, where are your maximums? So that looks like a min, because we're going down the nub, and then up and down means a max. So our max is at x equals 19.1. Our min is at x equals 0.87. So that's all stuff that we found from our first derivative. Now let's look at our second derivative. So our second derivative is 0 at 10. So right here at the 10. So we need to test the point on either side. If I go to the left, my second derivative is positive or above the x-axis. To the left, it's negative or below the x-axis. And so we're kind of going in an upward shape, and then, or upward U, and then downward U. So concave up, concave down. So concave up for x less than 10. Concave down for x greater than 10. Notice my concavity did change. Anytime your concavity changes, you have an inflection point at x equals 10. And that's what we can tell from the shapes of the graphs. Now next, this is kind of a tricky part the book puts in. Okay, and it kind of goes against your intuition a little bit. So how are concavity and slope related? So if our original function is concave up, that means our slope is increasing. So here's an example where our original function is concave up. So this is our original function, f of x. Okay. But if you look at it and you look at your slope, let's see what our slope is. So our slope is really steep, less steep, less steep, less steep. So it's getting less steep, but in a negative manner. So that actually means less steep negative is smaller, or negative numbers that are closer to 0. So slope is actually increasing. And over here in this function, so this is our original function f of x, and if you were to draw in your slope values, it looks like we are not very steep, more steep, more steep, really steep. So getting more steep negatively. So for negative, that's close to 0, further from 0, further from 0. And so our slope is decreasing. But you can kind of puzzle out, or you can just kind of remember this. This is one of the few things I actually tell you to remember. It's easier than trying to do the logic of it. So if your original function is concave up, slope is increasing. If your original function is concave down, slope is decreasing. So these are the same pictures we just looked at, but I just want to do them again. Notice on this picture, okay, we figured out we're concave up. and then we were, oh, not concave up, concave down. And then over here we're concave up. Okay, now look at your slopes. Our slopes went from 18 to 6 to 2. That means our slopes are getting smaller. And then we went from 2 to 6, so our slopes are getting bigger. Or if you look at these numbers over here, here's our 4. Okay, notice our slopes, because our slopes are the actual values, we were getting smaller, and then we were getting bigger. So this is an actual problem from the book or something very similar. So we have this function g of x that's shown below. It doesn't matter if it's f of x or g of x, that doesn't change anything. Use just the graph to determine over which intervals the slope is increasing or decreasing. So notice this is our original function g of x, but we want to figure out things about our actual slope. Okay, you could try and figure it out. You could say, okay, that seems really steep, less steep, so I'm decreasing. But really, it's easier to say that we are concave up and concave down. Let's just figure out where were those things. You can do that looking at the picture. So from here to about here, we would be concave down. So for x less than b. And from here to here, we'd be concave up. And so that means, and well, anytime you're concave up, slope is increasing. And if you're concave down, you have slope decreasing. And that's a lot easier than trying to look at the picture and figure it out each time. Now, another page of nitpicky things. So these, you should actually remember all of these from your Math 1050 class. But if you don't, here we go. If you remember, you can probably just skip ahead a little bit. So when you're describing shapes of graphs, we've talked about maximum and minimum, increasing, decreasing. Sometimes we also want to talk about the intercepts. So you have x-intercepts. X-intercepts are anytime you cross the x-axis. So cross the x-axis. To find those, you set f of x, our original function, equal to 0 and solve for x. Your y-intercept is when you cross the y-axis. So you plug in x equals 0 into f of x and you get your y value. So that one's the easy one to find. Okay, horizontal asymptotes. To find horizontal asymptotes, that's if you are getting closer and closer to something as you go towards an infinity or a negative infinity. And so to find that mathematically, you can look at these limits where x goes towards infinity or negative infinity. And if you get a number out of it, then you have a horizontal asymptote. Vertical asymptotes are where we would be dividing by 0 and you can't simplify or get rid of it somehow. You have a possible vertical asymptote. You also sometimes have undefined points on a graph, and that's points that result in mathematical errors such as dividing by 0 or taking the square root of a negative. So like if you have y equals square root of x, you can only take the square root for positive numbers. So x is only going to be defined for values greater than or equal to 0. Notice that my graph doesn't continue past that point. So let's try it. Most of your problems we're not actually going to ask you to find the intercepts and asymptotes, but I think there are a couple on your homework where you have to. So f of x equals x squared minus 3x minus 4. Find any intercepts. So let's do our x-intercepts. Let's do 0 equals x squared minus 3x minus 4. Solve for x. X is going to be, if you work it out, negative 1, or x equals 4. Okay, I'm not going to work them all out here to save time. So x-intercepts, that matches with what I have on my graph, negative 1 and 4. For your y-intercept, you plug 0 into f of x. So 0 is going to be 0 squared minus 3 times 0 minus 4, which is negative 4. Oh, that matches what we see on the graph. Now, check for any asymptotes. So for a horizontal asymptote, you want to look at the limit as x goes towards infinity of your function, x squared minus 3x minus 4. Okay. notice we can't simplify this in any way. It's not rational, we're not factoring, we're not simplifying, we're not canceling. There's nothing you can do to this expression to simplify it up. So if I was to try and plug infinity, I'm going to get really, really big numbers, minus really, really big numbers, minus really, really big numbers. But we have really, really big numbers here first. And we haven't done a lot of limits to infinity. It's okay if you don't really know how to do this yet. But basically we're going to have really, really, really big numbers, so we're going to get positive infinity. But if you look at the graph, notice you're going up towards infinity. That's not a number, so no horizontal asymptote. Similarly, if you checked towards negative infinity, sometimes you could just have one at negative infinity. You'd put in a negative infinity, but a negative squared is still a positive number. And the rest of this won't even matter because infinity got so big when you squared it. So you're still just going to get positive infinity, right? On the side you go to positive infinity. So no limits. And now for vertical asymptotes, you shouldn't see anything on the graph, right? So I suspect there isn't anything. But vertical asymptotes are where you have a mathematical error. But if you just have x squared minus 2x minus 4, there's nowhere you're going to get a mathematical error. So no math errors. So no vertical asymptotes. Let's try this next one. So f of x equals x minus 2 over x plus 1. Okay, so x-intercept. You set it equal to 0, so 0 equals x minus 2 over x plus 1, and solve. And so you multiply both sides by x plus 1, and so that's kind of gone. So you just have 0 equals x minus 2, so x equals 2. Okay, here's my 2, that's my x-intercept, that looks good. For y-intercept, you plug 0 into f of x, so f of 0 equals 0 minus 2 over 0 plus 1, which is negative 2. There's my negative 2. Okay, that sounds right. Okay, now for horizontal asymptote. You take the limit as x goes towards infinity of x minus 2 over x plus 1. Now later on in this class we actually are going to deal with limits that go towards infinity and we'll pay more attention to them. For now we didn't spend a lot of time on them in the textbook or homework, but I could try and plug infinity here, and I'm going to get infinity divided by infinity, and we don't really know what that is. But I'll show you a trick. You don't really have to remember this trick. Okay, and that's okay. I don't expect you to remember it yet because you need more practice. But what you can do is you could go through and you can divide every single term by x. Divide everything by x. And as long as you divide everything by the same thing, it's not changing, right? So you'd have x over x minus 2 over x over x plus 1 over x. And let's simplify. So we get 1 minus 2 over x over 1 plus 1 over x. Okay. Now if you try to plug infinity, you'd have 1 minus, now this 2 over infinity, so you have 2 divided by really, 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 really big numbers, and anything divided by really, really big numbers just gives you 0. And then we have a 1, and 1 divided by really, really big numbers gives you 0. So 1. So we actually do have a horizontal asymptote. As x goes towards positive infinity, we get closer and closer to 1. Pretty cool, right? And the limit as x goes towards negative infinity of x minus 2 over x plus 1. So simplify along, same thing. Dot, 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 you get to 1 minus 2 over x over 1 plus 1 over x. Okay. Notice here are 2 over really big numbers. It doesn't matter if they're positive numbers or negative numbers. It's still just going to go to 0, both of them. So we just get 1. So we do have horizontal asymptotes at y equals 1. Okay, notice that on the graph, we get closer and closer to 1, closer and closer to 1. And vertical asymptotes, That's when would you divide by 0? So we divide by 0 if f of x equals x minus 2 over x plus 1. We'd be dividing by 0 at x equals negative 1. And notice there's nothing we can do to simplify or not divide by 0. So we do have this vertical asymptote at x equals negative 1. And finally, section 2.3 in our textbook discusses how to take everything we've learned and sketch a rough graph of f of x if you're just given the equation f of x. We don't really focus on that partly because you can't actually sketch things in my math lab very well. Okay, but it's still kind of useful. Read through it, look at it, it will still help reinforce the concepts of what we've already learned.